So welcome back. Happy Thursday. We have the rest of example 7 to finish, looking at time invariant predictors in a piecewise model of growth is what we've been doing. We're going to finish one last model of that kind and then do a quadratic model of growth instead, which is what your homework 8 will have. So you'll get yet more practice with linear terms and quadratic terms that way. So time invariant predictors, let's do some vocabulary. Give me synonyms. How do you refer to a time invariant predictor? What are some other words? Between person predictor, sure. Level 2. Person level is one I use for people who aren't familiar with multi-level modeling. Person predictor, between person. Cross-sectional would be another one. Something that's measured only one time is the key. So we've been putting these predictors into our level 2 model. The logic is that any level 1 term, so here, for example, in front of me I have 3. I have intercept, slope 1, 2, and slope 2, 6. Any level 1 term for which there is random variability as part of it that we already tested for and found, and so we kept it in the model, those are candidates to have level 2 predictors of them. So in other words, because we found both of these random slopes to be significantly varying across people, it makes sense to try and find out why. So this is the explanatory part, the part where we're actually explaining variance, not making new piles. And as we talked about last time, level 2 predictors cannot have random effects in 2-level models, so we don't have to worry about testing for those. So this example then, yeah, question?
Maybe you finish explaining that one first.
I was going to jump into education, so if you have a question.
Yeah, that's my question. Why didn't you explain first?
What did I do what?
I was about to ask about the education. Because on the level 2 there are 2 of them.
Yes. So this is education group. And remember, I took a continuous predictor and I cut it up into 3 groups just so that I could show you what it would look like if you had a grouping predictor. Even though I would never do that in life. It's a bad idea to take variables and cut them up. But we have 3 groups. So that means to represent 3 different means, we need 2 contrasts. It can be any kind of contrast that you want, but we need 2 of them. And so that's why you don't see the word education as a predictor here. I have written out the contrasts that the model is going to fit for us because we are putting education group on the class statement. So when you put it on the class statement, the last group, alphabetically or numerically, is the reference. So in our coding, 1 is low, 2 is medium, and 3 is high. That means high is the reference. And so I've written these contrasts to be high versus low and high versus medium because that's exactly what the model is going to give us. When we get down to the fixed effects, you'll see that the 3 group is zeroed out. That means they're the reference. And then each of the other coefficients is how 3 compares to 1 and 3 compares to 2. So I wrote the model in the same way that SAS fit the model. Does that help? Yeah, okay. Other choices, what else could I have done? I could have put these in as continuous, created my own dummy codes like we did for dementia group. Another type of contrast that I sometimes use doesn't make as much sense in this group, but for example, so you get bonus points for showing up. I'm going to write on the board, let's say that you have something like group 1 is a majority group of some kind. Group 2 is some kind of minority group, let's call them minority group A, and group 3 is minority group B. I've seen people with these sorts of studies before. So an obvious choice to make your coding would be to do something like this, where you have the majority group as the reference, and you create one contrast that would give you majority versus minor, so 0, 1, 0. and another contrast that gives you majority versus minor B, 0, 0, 1. That's fine. I could switch around the reference groups, but to get minority A versus minority B, I would have to either change one of them to be the reference, and then it would be given directly, or I would take their coefficients and subtract them. Right? The coefficient for this variable minus the coefficient for the other variable gives me the difference between the non-reference groups. But what if you want to know if being part of a minority group is just different and it doesn't matter which group you're part of? That might be a reasonable question. So if I want to know that, I'm going to do something different. I'm going to make the majority group my reference again, but I'm going to code both of minority groups 1 in one of my contrasts. Then in the other, majority group is still 0, but I'm going to go minus 0.5 for minority A and positive 0.5 for minority B. Then I get two effects that says, what is the effect of being majority versus any kind of minority? That's one answer. And then within the minority groups, what's the difference of being A versus B? And if you find, for instance, that it doesn't matter if you're A versus B, but it does matter that you're in one of those minority groups, you could drop the second contrast and go on with just the first contrast. But either way, there's 2. You only need 2, and you can always get to the third. So the dummy coding that SAS does for you by default is convenient. It may not be the most direct way to answer your questions. So just think about that as you have the flexibility to treat these groups however you like. So, little bonus for the people showing up to class today. So the other stuff that's on here looks a little bit different because we've used the class statement. So I've done this right here. The total set of effects of education, there's 6 of them. Because I have 2 contrasts for the intercept, 2 contrasts for slope 1, 2, and 2 contrasts for slope 2, 6. Now the pattern in which I am asking for those 6 effects looks like contrast coding. For each term, I list 2 contrasts. So for instance, these first 2 refer to the effect of education on the intercept, and I'm doing the difference between low and medium and low and high. Which contrast I put in here doesn't matter. I only need 2 of them because that's all you need to get to the third. So as long as these aren't identical, you'll get the right answer. And I did the same thing for each of the other sets. So on the whole, this is going to give me a multivariate test of whether education matters. By default, because I put education on the class statement, I will get the test multivariate for each type of effect. I will get a 2-degree of freedom contrast for the main effect of education on the intercept, another 2-degree of freedom for its effect on one slope, and the other slope's 2-degree of freedom test as well. I get that already, so I'm not asking for that extra. Other things that I am asking for that you haven't seen much of, so I'll go over those. LS means gives you adjusted means or conditional means for each group. And I am holding the covariates constant to the levels at which I want to condition on. So the first line, by putting zeros everywhere, I am saying I want the education group means at the first occasion, because that's when slope 1, 2 is 0, and that's when slope 2, 6 is 0. And I want them for my reference person with respect to the other covariates, an 80-year-old with average reasoning. And then diff equals all is going to give me the pairwise differences between those 3 adjusted means. The next line then, what does it mean when I code slope 1, 2, 1 and slope 2, 6, 4? What am I asking for? What occasion is that? It's the last one, 6. Yep. How do I know that? Let me go back to the very beginning where I created my slopes. Slope 2.6 is session -2. So if I give it a value of 4, that means I'm asking for session 6. And at session 6, slope 1.2 retains its value of 1. Why am I asking for that? That's one way that I can try to illustrate the interaction, is how the group differences change over time. So I'm getting the group means and the group differences by which to be able to describe that. The other way that I can talk about the effect of education interacting with time is by saying, how does the trajectory change as a function of group? And so the last set of contrasts here give me the difference in each term as a function of group, where the first two are actually given by the model already, but they're here for completeness. And the third one is the one that is implied but not given. It's the difference between the two non-reference groups. And so I have those three sets of contrasts. Now, one thing that isn't here that also probably would have been helpful. I know, according to the model, whether each group has a significant time slope if they're in the high group. The model does not tell me whether each group has a significant time slope if they're in, I am in the wrong one. Hang on, I scrolled too far. Let me find the piecewise models. Sorry. Here we are. Same pattern, different set. I don't know what the significance of the other group's slope is, so that might be something I might want to add. For instance, we'll just do this on the fly. Come on. Copy. Paste. So, what if I did something like this? Low education slope 1.2. I need, since I'm asking for slope 1.2, I need that first. Let me get the colors right here. And I would need to zero out the other groups. If I want to do medium, what do I change? And I move this over here, right? Do I change this one? Nope, this is the thing I want. Who do you want it for? Changes. That's the second part. So we'll make this one 0 and that one 1. Would I need to write one of these statements for the high group? No, Kofung, you're shaking your head? You're right. Why don't I? What? It's implied. Well, I already have it. So because my high group is the reference, the main effective slope 1.2 is for that group already. So I don't have to ask for it. But I could, because then they'd all be in one place, which is convenient. That's the trail of breadcrumbs approach, right? Don't make yourself figure out something multiple times. Figure it out once and write it in a way such that you can refer to your own figuring later. So that would be a 0, and that would be a 1. And if I wanted to get the slope 2.6, 3 more statements, swapping out the variables here and here. But what I had done for you is just the contrasts of the slopes between the groups. Okay, so here's my solution. I try to get as much on the page here as possible. There, that's almost got everything. So the top 3 rows there, that's my reference trajectory. In addition to being for an 80-year-old and someone of average reasoning, it's for a highly educated group. The effects of age and reasoning are now controlling for education, but they are not conditional on education because they don't interact. I get the model provided contrasts for the intercept and for each slope here, high versus each of the others. So for instance, the low educated group starts out 41 milliseconds faster than the high educated group, but that's not significant. The medium group starts out 25 milliseconds slower, but that's not significant. And the same pattern happens for these. The difference between high and each of the others is not significant. I don't know yet about 1 versus 2 because I have to ask for that one. But down below, I do get the simultaneous test of each of the two contrasts for the intercept and for each slope. That tells me overall, is there an effective education on the intercept? No. Overall, is there an effective education on slope 1, 2? No. Overall, is there an effective education on slope 2, 6? No. Here are the rest of my contrasts, and the missing one is low versus medium. So for instance, this 67, where that came from is the difference between this minus 41 and this 25. That's what it did for me. You can always get the missing contrast by subtracting one group difference from the other. And then finally, my 6th degree of freedom contrast for, is there any effective education of any kind? No. So it doesn't look like it matters. Here are the means that I asked for at the beginning of the study and at the end, as well as the mean differences between groups. So these ones are the same as the group differences on the intercept because that's what this means. This second set contains new information because these are the group differences specifically as predicted at time 6, session 6. Nothing here. Unsurprisingly, our total R-square increased by 1%, and all of our random effect variances actually went up a little bit. So that will happen when you have something that's really non-significant. And this is why this term is called pseudo R-square, not R-square. It's like R-square-ish. Oh, I did do age by reasoning for you guys. So remember I talked about this last time and I was all, hey, I was nice, I didn't do it. Yeah, I'm not nice. Yeah. So I tested age by reasoning just to give you some more practice with two-way interactions. And by two-way interactions, there's only one of those that I've added. These last two, those are three-way interactions. It's age by reasoning by slope 1, 2, and age by reasoning by slope 2, 6. So now, the effects of age are not only after controlling for reasoning, but conditional on reasoning, which means they would change at different values of reasoning. Likewise, the effects of reasoning are conditional on and controlling for the effects of age. And so here's some examples of how you would try to explain those two- and three-way interactions. So for instance here, I've got, what is the age effect on the slope, or the intercept, excuse me, at different levels of reasoning, where these are low, average, and high. So age comes first, because that's what I want to know. Reasoning is the modifier, so that's what I fill in the values for. Likewise, the effect of age on the slope 1, 2 is what I want to know, so that's a 1. I fill in the values for reasoning as the modifier. And same trend for slope 2, 6. The code in the second half is analogous, but it switches which slope is of emphasis to be reasoning. So now the values that I fill in for the reasoning by age interaction here correspond to the ages I want the reasoning effect for, instead of the reasonings that I want the age effect for. It's always the other one that you fill in the values, the other one besides the slope of interest. And so this may help me explain any three-way interactions as talking about how the two ways change as a function of some third variable. So let's do some practice with the three-way interactions here. My spacing is all screwed up because I added some stuff to the file, so we'll just move this so we can see it on one page. Okay, so here's my age effect at session 1. That's for reasoning 22. What happens to my age effect as reasoning increases? Less positive, or in more friendly terms, weaker? Your age effect is weaker. How about if we go the other way? Reasoning effect is for an 80-year-old. What happens to it in older people? Stronger, more negative. So yeah, you can't just look at the sign of the interaction and know what it's doing. It has to be related to the main effect. A negative interaction can make a negative main effect stronger, or it can make a positive main effect weaker. Let's do slope 1, 2. That's slope 1, 2 for an 80-year-old of average reasoning. What happens to it in older people? Can you see the signs? Yeah, make it bigger. What happens to the slope 1, 2 in older people? More negative. So older people decline more quickly. And then, what does reasoning do to that? Yeah, less more quickly. Right? The extent to which older people change faster is reduced in smarter people. The extent to which is a great way to start a two-way interaction, because then you're describing that pattern already. The extent to which older people change faster is reduced. Let's go the other way. Here's slope 1, 2. There's slope 1, 2. What happens to it in smarter people? More negative. So smarter people decline faster. And then what does age do to that? Slow it down. Yeah, less so. Yep, less so in older people. Less, more negative. So you guys are getting really good at this. Have you experienced righteous boredom yet? I don't know, you two look like you might be suffering from righteous boredom. Do you know what that is? Righteous boredom is when you're like, yeah, I get it, move on, and you're bored because you're following, as opposed to boredom that's like, I'm never going to get this, I'm not going to listen anymore. Right, righteous boredom. Are we righteously bored yet? No. Not yet? Not yet. See, I harp on this because I get really frustrated when I read things in manuscripts like age-moderated reasoning. And that's the end of the story, right? Moderated. That could be one of 8,000 different patterns. The fact that it moderated does not answer a question of any kind, because the pattern of moderation could be completely counter to what was expected. So if you're going to test moderation, the onus is on you to explain it. It's helpful to talk about what happens to the coefficients. It's helpful to give them simple slopes. Like for example, the effect of reasoning for a 70-year-old on the intercept, or on slope 1, 2, that's what we're doing, is minus 15, whereas it's negative 3 for an 80-year-old. Those can make those ideas a little more concrete. You can make a picture that has different slopes for different folks. That would be another way to do it. A lot of people get scared by like three-way interactions and they don't even try them. That's not a good reason not to try them. There's nothing to be afraid of. Now we have a pseudo r square here. Which term should have reduced the intercept? And I say should have because it didn't, but it should have. So I've got three new terms: age by reasoning by slope 1, 2, age by reasoning by slope 2, 6. Which of those three should have reduced the intercept? Age by reasoning by itself. Which of the other two should have reduced the slope 1, 2 variance? This one right here, this UN2, 2. That's slope 1, 2 variance. Don't think too hard. Your choices are age by reasoning by slope 1, 2, or age by reasoning by not that slope. Yes, slope 1, 2. And likewise, age by reasoning by that slope should have reduced that variance. Everything is nice and orderly whenever you're in a situation like this, where each level 1 effect has a corresponding random variance. If there's a U at the end of the line, anything that goes in the line explains that U. It's very straightforward. But what would happen if, say, slope 2, 6 was fixed and that U wasn't there? Some people would say you can't do that. I say you can do that so long as you've tested slope 2, 6's variance first, and you include it if you need it, but if you don't, okay, let's take it out. What would these fixed effects in this line have to do? What's left? This is really uncomfortable holding my arm like this, so can someone answer, please? Yes, I'm double jointed. You can see my freakishness. Yeah. I was on dance team in high school, and there was one type of move that we called this a high V. And like I have to rotate my shoulders in, otherwise my V is broken, like by default. And it's really gross. So I'm like, high V. But anyway, here we go. Tell me, what's left? What do the fixed effects in the line for slope 2, 6 have to do if there is no random variance for slope 2, 6? E. Those level 2 cross-level interactions, and level 2, yeah, this one is still cross-level because of the slope 2, 6. They reduce E if they don't have a random variance to reduce instead. So cross-level interactions, the things we're talking about right now, anything that interacts with a slope, they explain E variance if that slope is not random. Think about the original version of the model. Once upon a time there was an E, right? And then we made two piles. And then when we fit a random slope, where did that come from? It came from E. So it's like it's still in there. There's just not enough of it to warrant pulling it out. if there really is no slope to 6 variance, I think you are okay testing this with okay type 1 error if there really is none here. The trick is making sure that you haven't made a type 2 error. So the idea that I've been working on papers is trying to find ways of using some kind of effect size as opposed to just significance to make sure that you're minimizing type 2 error and you're not keeping the slope. But do you remember the term that we would use for slope to 6 if this U2 random effect wasn't here? It's systematically varying. Yep, non-randomly or systematically varying is what I would call slope to 6. Does everybody need their own? Only deterministically as a function of age and reasoning. After that, people of the same age and the same level of reasoning do not need their own. So the slope is not fixed. It's not that everybody gets the same. It's not random if this weren't here. It's that it's systematically varying, non-randomly varying. That's what you would call it. And if you need an excuse to be able to do that, you can cite chapter 7 of my book. How's that? Yeah, driving up the citation rate. Woohoo! Well, you know, when you spend 5 years doing something, you kind of want it to matter. Just a little bit, you know. I get like $1 for every book I've sold. Like, I'm not getting rich off it. This was a labor of love. You think I'm kidding, but I'm not. The publishers make all the money, not the authors. So, unless you sell like a, you know, introductory stat textbook or something where there's a whole lot more people buying it, then you could get rich. But there's 1 million of those books already, so I don't have any interest in writing those. So, anyway, back to the models. Do you want to see quadratic? Quadratic is trickier because then you have things that change. When you interact with quadratic, what it means is that the effect of the predictor changes non-linearly over time. And Ori, we were just talking about this, right? So this one's for you and for homework 8. So we're starting in our quadratic model, same data, just a different model of change, so you get practice with this kind. No predictors. Why do I do this? Why would I start here? And why would I report this model in practice? It's a baseline. It's unconditional model of change, yes, or unconditional growth model, whatever you want to call it. The term unconditional means addressing time, but without considering other predictors. So these U's here are as much variance as there is to be explained in the intercept, linear time, and quadratic time slopes. So it's my new baseline. So I've got, here's my model, here's my baseline. I've explained about 4% of the total variance. Do you remember where this number comes from, this total R squared? Remember how to get this? You get to get it in homework 8, so you better answer. And if you don't remember, say, I don't remember. Can you tell me again? Do you remember? That's it. So we're asking the program, and all programs will do this, by the way, if you know how to ask for it. We're asking it to save a column of predicted outcomes from the model fixed effects only into a column into a new data set. So it takes your current data set and adds these columns to it. That new column is called pred. So then I'm asking for a correlation then, just a regular Pearson correlation between that predicted column and the regular outcome. That's R. You then square R, and that's R squared. So I find this to be a useful supplemental piece of information because it gives you sort of an overall sense of how your variables are working. It makes less sense in contexts in which the predictors that you're focusing on only could possibly account for a small part of the variance. So in models that have a lot of variance components, and I think it would be very cumbersome to keep track of them all, I'll go this route for effect size. It's up to you, so long as you say clearly in your beginning what you're doing and give them the formula. Tell them what it means, and then they can judge for themselves whether that's informative or not. So here's age, adding age to the story. Gamma 01 on the intercept, 1, 1 on the linear time slope quadratic. So the level 2 equations are going to look identical to what we just did. The only way I know what beta 1 means is because it's defined in the level 1 model. Previously, beta 1 referred to slope 1, 2. Now it's linear time. When I write out these equations, I started doing this in the book and I've kept doing it since then. I find it helpful to remind the reader what this is the equation for, just to make it as concrete as possible. It doesn't take much extra room, and I think it helps with interpretation. I'm then asking for the age effect at each session, as well as how the age by time interaction varies by time. Let me say that again. That's what makes the quadratic models harder. I have age as a moderator of the linear time slope, and I have age as a moderator of the quadratic time slope. So I can talk about these results as what happens to the trajectory for people of different ages, where the trajectory is characterized by these 3 terms. I can do that way. Another way to talk about it, though, is to focus on the effect of age and how it changes over time. How it changes over time is a function of 2 things, not 1. So it can be tricky to explain that. So that's why I wanted to explicitly do an example with quadratics so that we get some practice. So let's take a look. Here's our model. It's been a while since we did quadratics, right? But you guys remember the rule? So the first 3 lines, that's my reference trajectory. In this model, it's for an 80-year-old. Given my coding of time, the intercept is the beginning still, so 1950 milliseconds on average. This linear time slope means what? This 121, minus 121. It's for an 80-year-old, I know that, but beyond that, what is it conditional on? So there's a special calculus word that goes with this. Do you remember? It starts with an I. The slope of the line that's tangent to the curve at session 1, instantaneous. This is the instantaneous linear rate of change. In physics, you'd call that velocity and acceleration. Remember this? I took physics in high school and then went, never again, I hate this stuff. But then I'm like, oh God, I guess this does matter after all. But yes, this is the instantaneous linear slope at session 1. What happens to it over time? What does the quadratic do? Yep, the linear rate of change becomes less negative by how much a session? And don't say 13. Is it half or twice? Twice, yes. This is a homework question, by the way. I'm going to try and trick you. The quadratic term itself is half the rate of acceleration. So to talk about how the quadratic changes the linear slope, it's twice the quadratic to get to the full rate of acceleration. So it becomes less negative by like 27-ish per session. So that's my reference growth curve. Now let's find out what age does to it. Age makes my intercept, and this, since it's a main effect, you can just say higher or lower. older people are slower. This is response time. Significantly, right? Which variance component does that significant effect explain? What's my effect size? Let me back up. Main effective age, the 29. Where is that in my equation? Which gamma? Gamma 0, 1. Therefore, which variance did it explain? What is that? Random intercept variance, yep. Main effects explain intercepts. So the main effective age is 29 at session 1. What does age do to the linear time slope at session 1? So we're linear time slope is minus 121 for an 80-year-old. What happens to it in older people? Yeah, this is a minus sign, so it's more negative. Yep. So older people decline faster initially. Their slope is steeper. What happens to their quadratic? Quadratic is 13 in 80-year-olds. What is it in older people? More positive. So let's put that together. What does it mean to have a more negative linear slope at session 1 coupled with a more positive quadratic? Can you do that in your heads? Because I can't. It's kind of like, right? Then I'm like, uncle, I cry uncle. You know what I do? I make a picture. So we'll have a picture here momentarily that explains that. But the general tendency is that, yeah, they decline more, but the rate of that decline slows down more. So it's a greater rate of deceleration, if you will, but non-significant. So, but I don't care about significance. I want you to know what to do with the numbers. So that's one way to talk about this pattern, is what happens to the trajectory as a function of age. I think that's the most intuitive way to do it. But instead, if what you're interested in are age differences and how age differences are changed by practice, remember these are 6 sessions of practice. That's the goal here, is to see how these older people improve in this task. If I want to know how age differences are changed with practice, then what I'm doing is starting with this main effective age and talking about what happens to it over time. And Ori, you want to talk about the effect of gender and what happens to it across grades? Okay, this one's for you. So this is the main effective age at session 1. Also at session 1, what does this time by age interaction say happens to it? So we're doing these two together. Main effective age is positive at session 1. It becomes what, according to this interaction? Less positive, but this interaction term is also at session 1 because it's conditional on this one. So it's positive, like simultaneously becoming less positive in older people. And then what happens to it? Exactly. I'm going to go with less positive. Think I'm right? This is why we asked for these estimate statements This first set tells us what happens to the age effect at each session, so if I can see if less positive is right. The second one tells us what that time by age interaction itself is predicted to be at any other session. And note, for these, it's time times 2. That's what's filled in here to get to how the time by age interaction itself changes over time, whereas it's time squared that's filled in up here because the unit that we're trying to get the slope for is age. So you fill in time and time squared as moderators of age. So let's look at these estimates then. So the age effect at each session, 29 is where we started. As you go down, it's less positive, right? But as you keep going, it's less positive. I win. So the effect of age changes quadratically over time. That's another way to think about it. The next set of estimates then give the model predicted age by time interaction at each session, where the first one is what's up above in the model, and then the difference between these is constant. It's twice this number right here. Let me see, did I make a picture of reasoning or age? I'm trying to remember. Yeah, I made a picture of reasoning because that one was actually significant. So we'll look at that picture instead. It's the same pattern. Okay, so we did the interpretations. Here's my 3 degree of freedom wall test for the overall effects of age. So that 3 degree of freedom test I can think of as the significance test for the change in total R-square between models. By adding those 3 fixed effects of age, we have picked up another 7% of the total variance. So the total R-square macro that I wrote, you can do these calculations yourself or you can use it. You fill in which DV you're using, the predicted values from a model that's simpler, and then the predicted values from the model that's more complex. And then it gives you the R-square for each model as well as the difference between the two. Then we have our pseudo R-squares. 10% of the intercept. That goes with the main effect of age. About 3% of age by time, or the time slope that goes with age, and less than 1% of the quadratic time slope that goes with age. Okay. How are we doing? All right. Adding reasoning. Same exact logic, just swapping out the variables that we're focusing on, keeping age in the model so that I can say I have control for age, adding the effects of reasoning. The pattern is similar, although the effect of reasoning itself is negative. If we look at these coefficients right here, that minus 27 is the effect of reasoning at the beginning. What happens to it over time? Initially. This is a more negative, a stronger. However, what happens to the more negative as time goes on? Yeah, less more negative. The more negative slows down, yeah. So the implied reasoning effect at each occasion then is biggest in the middle. It's more negative, but then that more negative slows down and it actually ends up reversing direction. So this coefficient eventually overpowers it and flips the direction because it's so big. And here's my picture. So this gives me different trajectories for different levels of reasoning. So the people who are the slowest are the people with the lowest amount of reasoning. The people who are the highest are the fastest. They get more faster initially. So the difference between these lines is biggest in the middle, and it starts to narrow again as time goes on. Yeah.
So in the when we are writing a report, does that last one, the quadratic make sense? It's like you practice more than you just.
And there's the problem with quadratic models, yeah. I mean, these are model implied trajectories, right? So they're all predictions. They're all subject to saying how well does this model fit in an absolute sense, and we don't really know that. But yeah, this implies that the people are going to come back up again. And that face, yes, exactly. She's dissatisfied with that, I can tell. So am I. So what would be better, potentially, would be to fit a model that either has an asymptote, that's a regular non-linear model that predicts this to sort of level off, or to cheat your way there by logging time and putting in linear and quadratic effects of log time, which greatly diminish the amount of, like, it takes much longer for it to come back up. So next time in the book, I'm going to add that log time. So, all right. So reasoning in this example doesn't have the same special status that age does for me. Remember my story from last time? Age is one of those variables in the world of cognitive aging that you have to control for or someone's going to yell at you. That's just the rule. And I am leaving in all of these non-significant interactions because I want to say that I've controlled everything for age that I need to. But reasoning doesn't have the same status. So what do you think? Should we dump both of these? They're both non-significant. Or should we dump them one at a time just to make sure? One at a time, feeling conservative? Well, which one do we start with?
Slope. I mean, the linear slope.
Well, the linear slope has the higher p-value, so normally I'd agree with you. However, yeah, these are hierarchical. So we have to dump the highest order one. So let's get rid of reasoning by quadratic and see what happens. So I'm going to leave that right here so you see what happens at the top. Okay, so my new model is at the bottom. This is something that I do because I think it helps, but it may be weird. I maintain the spacing so that you can see that something's not here that could be. I also skip numbers. Like if I had 02 and 12 and then I added some other variable and it was going to be 0313, I would make it 23 to keep it the same. That way I know that 3 always refers to that variable even though there's no 22, because there could be. So that's just conventions that I follow to try and keep these things organized. So here's my new model with just reasoning and reasoning by time. Ta-da! Take a look at that. Yeah. So yes, you can't see the very bottom here. The reasoning by time interaction that used to be, where does it go? Oh, hang on. I gotta scroll more. There we go. I'm gonna hold that right there. Now you can see. P-value of 0.42 versus p-value of 0.02. Ah. Surprising? No? You're not surprised? Are you surprised? You're surprised? There's no right answer to that question. But think about what you learned about collinearity and regression among predictors. You think age by time and age by time might have something to do with each other? Yeah, kinda. One's almost a linear combination of the other, but not quite. So if we look at the standard error for these things, the standard error was 4.4 up here, it's down to 1.26. And the coefficient has changed completely. It was negative 3.6 and now it's 2.3. So it's really not the same in any regard. It doesn't mean the same thing. The negative 3.5 at the top, that was the age by reasoning slope at session 1. Reasoning by time at session 1. The bottom is reasoning by time on average. So we computed simple slopes. Let me see here. For what the reasoning by time interaction would be, as implied by reasoning by time. So this is what the model said it would be. Note that the ones in the middle have the lowest standard error. They're the ones that have the most precision, because wiggling the slope doesn't change the middle as much as it changes the ends. So this time by reasoning of 3 is kind of like the average, or 2.9. It's kind of like the average of what used to be here. It's the average age by reasoning by time. So it means something different. It's tested with more precision because we don't have reasoning by time fighting against it, so it's a different result. So point of the story, when you're in the situation where you have quadratic interactions and linear interactions, don't dump them both at the same time. Drop the quadratic first, see if the linear comes back. That's the moral of that story.
Is it very common to see such sensitive change when we're dealing with the quadratic?
Yeah. For that reason, sometimes people prefer to mean center time, because that reduces the collinearity between the linear and quadratic terms, but it also changes the interpretation, because then everything is referenced to mean time as opposed to session 1. So you just have to keep that in mind. One thing that you don't want to do is like have time be centered such that session 1 is 0 and then mean center time in the quadratic interactions. Don't do that. You have to keep it consistent throughout the model. There has to be the same time 0 everywhere. What else do we have in here? Oh, education. Yeah. So yeah, this is what I was saying before. In terms of my equations, I left the hole where reasoning by time would have been. I do that so that it's obvious that it could be there and it's not, and I do that so that the numbering stays consistent. But that's just my own tendency. I can't say that's right or wrong, but it makes sense to me. Here's education. We did all of this before. Same result as last time. Education doesn't matter any way you look at it. Least squares, effect sizes are negative, and that's it. And, see, I told you guys I was not nice, but I lied. You know why? Words. Look at all these words I gave you. So this is the way I would write up this entire narrative. For the piecewise models first that we went through, and then for the quadratic time models. And so this is the type of thing that you will be completing in homework 8, where you will have the drop-down menus. And that's that. So questions on time invariant predictors? All right, then let me tell you about things that we're doing next week. As I told you, we have new materials. First, you're going to get an email later this afternoon from a Qualtrics account that I created. I am asking for your participation in a feedback survey for this class. There is a regular student evaluation that you do for this class that you should have gotten another email about. Those are generic questions that are used for the entire university, and they say things like, you know, how satisfied were you? Like, as an instructor, if you say, I hate this class, like, what am I going to do with that feedback? Like, why do you hate it? How could I have made it better, right? So I do my own survey filled with, it's just 10 questions, but I'm trying to ask about your experience with specific aspects of the class, what you liked about it, what you didn't like, what you would recommend for the future. To encourage your participation in this, I'm willing to give you 1 extra credit point towards your grade for completing it. I'm not kidding. The way it works, by the way, is that I give you a list of emails to Qualtrics, and I can download a spreadsheet that says whether or not each of you has responded, but your emails are not tied to your responses. It's set up to be anonymous. So I will know if you've done a survey, I just won't know which one you had. That is to say, please be honest. If you hated something, tell me. That way I don't have to inflict it on other people. Or maybe if you hated it and I'm like, well, I'm going to do it anyway because I had a good reason for doing it. But I do want your feedback, so look for that this afternoon. The stuff that we're going to do next week, I'm actually, we're not going to get started with Lecture 9 today. I was optimistic in thinking that would go. I decided to do that to be consistent with what's going on in the Bayes class. So I'm actually going to be giving, I think, part of Jonathan's lecture next week on these models. But the world of time varying predictors is where we're headed. So do you know what a time varying predictor is? Right, level 1. So we've seen time varying predictors, for instance. Let me get back to a model here. Here's a model. Are there any time varying predictors in this model? Session, right? Time is a time varying predictor. And we have talked about these fixed effects as this is within person linear change and this is within person quadratic change, right? No biggie. So what if I threw something else in the level 1 model that was measured at each occasion, such as a person's how they're physically feeling. These are older adults, right? They have health that's problematic sometimes. What if I had an inventory of physical health and I gave it to them every day? Sure, I could do that. Put it in a level 1 model, give it a fixed effect, maybe a random effect, and I'm good, right? Right? Nope. Nope. And this is something I've written about extensively. It's something that people still don't understand despite the fact that everyone has written about it extensively. You can't do that. And if you take my clustered class in the fall, I'll tell you why you can't do that in clustered data either. For the same reasons that we're doing all of this for response time, we're figuring out all the different kinds of variance in response time and we're assigning predictors that capture each kind of variance, we have to do the same thing for health. If health varies over time, then do you think some people are healthier than others? Sure. That's a random intercept variance. Do you think some people have better, or some days are better than others? Sure. That's residual variance. If we want to talk about how health relates to something else, then it's possible that healthier people do better at this task, that they're faster. That's a between-person relationship. And it's possible on days you feel shittier, you do worse. That's within persons. So for the same reasons that we have to worry about modeling level 1 outcomes, we have to model level 1 predictors. So there are observed variable approximations that people use to do this, where they take the mean of the predictor and stick it in the model, and they change the level 1 predictor to have only within-person variance, and I'll talk about those briefly on Tuesday. They're not good enough whenever your level 1 predictor is also likely to show change over time, which in longitudinal studies, chances are it does. So then what you really need is a multivariate model, where I've got a model for X and a model for Y at the same time. And so then you have your intercept for health predicting your intercept for response time, your slopes for health predicting your slopes for response time, your residuals for health predicting your residuals for response time. So that's what we're doing next week. Normally, that's the very, very end of a 2-semester sequence of classes that I do, and I'm throwing it at you this time because I think you can handle it. It does require switching software, though. I'm going to be showing you stuff in M+. Are you guys familiar with M+? Is anyone not familiar? Never seen it before? You've really seen it? Are you good at M+, or you just like seen it before? Seen it? Okay. That'll tell me how slow to go through this stuff. So the materials for next week then have a little bit of SAS, but it's mostly M+, because SAS cannot do multivariate models where you have a predictor and an outcome. The only kind of multivariate models it can do is when you have 2 outcomes that are correlated. So it's very limited in that sense. So I have to switch software. So that's why you will see SAS and M+ files that go with this. So that's what we're doing next week. All right. Any questions? No? You want to go home? Yeah? Or go back to work, I guess? I don't know. Yeah? Okay, let's all do that. So I will see you next week. Quiz due, or homework due tomorrow, quiz due Tuesday that we'll go over as well. So peace out. See you later.